Dear students, in this class, let us discuss about intervals. So, you know that what is an interval? Interval means it is the order relation on R which determines a natural collection of subsets. Intervals are defined as it is the order relation on R that determines a natural collection of subsets. So there are different types of intervals: open interval, closed interval, infinite open intervals, and infinite closed intervals. So, what is an open interval? Open interval means letter A and B are any two reals, then such that A less than B. Then the open interval AB equals, it is defined as set of all x following R such that A less than x less than B. So this is the open interval AB. A and B are the n points. What about the next one is closed interval AB. This is closed interval. Closed interval AB is defined as it is a set of all x following R such that x ranges from A to B, or A less than or equals x less than or equals B. Now, closed open AB, half closed interval or half open interval. Closed open AB means set of all x following R such that A less than or equals x strictly less than B. Right endpoint is excluded. And open closed AB is set of all x following R such that A less than x less than or equals B. So this is the four types of intervals: open interval, closed interval, open closed, and closed open. Among these four, the length of an interval is always upper or right endpoint minus lower endpoint. It is the length of closed interval AB is B minus A, that of open interval AB is again B minus A, and both of closed open AB and open closed AB is also of B minus A. Now, what about open interval A? Open interval A is immediately it is an empty set. Open interval A, there is no element lies in between A and E, so open interval A is empty. And what about a closed interval A? Closed interval A means it is singleton set A, only an element A present in it. So closed interval A is singleton set A. Now, what about open interval or S? It is open interval A infinity. Right endpoint is infinity. Open interval A infinity is set of all x following R such that x greater than E. Open interval A infinity, that is if it is A, it is plus infinity and minus infinity, then this is the open interval A infinity. So it is set of all x following R such that x greater than E. Minus infinity B, open interval minus infinity B. Open interval minus infinity B means set of all x following R such that x less than B. Similarly, closed open A infinity. Closed open A infinity is set of all x following R such that A less than or equals x. Okay, A less than or equals x. And open closed minus infinity B equals set of all x following R such that x less than or equals B. So what is R? Actually, set of reals is R is open interval minus infinity, this one. R equals open interval minus infinity, infinity. So these are the intervals. So interval means it is the order relation on R that determines the natural collection of subsets. This is the definition, and these are the different types of intervals. The length of an interval is its right endpoint minus left endpoint. So now we discuss an important theorem. It is the characterization theorem. The theorem is known as characterization theorem. The theorem states that if S is a part of R, subset of reals, that contains at least 2 points and has the property if x comma y fall in S, x and y fall in S with x less than y, and xy is a part of S, then S is an interval. So this is the characterization theorem. If S is a part of R, x and y fall in S, x less than y, it contains at least 2 elements x and y, and interval xy is a part of S, or open interval xy is a part of S, then S is an interval. This is the characterization theorem. So there are different cases. Case first, S is bounded. S is bounded. Bounded means which is bounded above and below. So by completeness property, since it is bounded above, it has a supremum, as well as it is bounded below, it has an infimum. So we have to let A equals infimum of S. Infimum of S, and B equals supremum of S. A equals infimum of S, and B equals supremum of S. So A equals infimum S, B equals supremum S means S is a part of closed interval AB. Agreed? S is a part of closed interval AB. A is infimum of S, B is supremum of S. So clearly S is a part of closed interval AB. Now let us set the following number. Let set this in a real number, set the following R such that set fall in open interval AB. Set fall in open interval AB means A less than set less than B. Set fall in open interval AB, by the definition of open interval AB, set lies in between A and B. Now A less than set, consider this A less than set. But what is A? And A equals infimum of S. A less than set, A is the infimum of S means A is the greatest lower bound. So we conclude that Z is not a lower bound of S. Okay. A less than Z and A is the infimum of S. A less than Z and A is the infimum of S means Z is not a lower bound of S because A is the greatest lower bound. Enough. Okay. Now also Z less than B by the choice of Z less than B. And what is B? B is the supremum of S. So that means Z is not an upper bound of, that means Z is not an upper bound of S. Now listen, A less than Z and A equals infimum of S means Z is not a lower bound of S. Then there exists an X fall in S such that A less than X less than Z. Agreed? Okay. And Z is not, according to this argument, Z is not an upper bound of S. Since Z is not an upper bound of S, there exists some Y fall in S such that Z less than Y less than B. Z less than Y less than B. So combines means a less than x less than such. You can combine a less than x less than such and z less than y less than b. So combines what I get? It is x less than, come on, x less than z less than y. X less than z less than y. So x less than z less than y, and what about x and y? They are in S. X and y presents in S. Z is chosen from R, then but that Z lies in between x and y. That means Z less than x less than x less than z less than y means Z following open interval xy. Agreed. But what is open interval xy? That's a part of S. So Z following yes, but actually Z following open interval AB. Hence open interval AB is a part. Then S equals what is it? Open interval AB is a part of S. Z following xy is a part of S, but Z following open interval AB, that's a choice of such. Hence, we can say that open interval AB is a part of S. Agree. Now, if A fall in S, if A presents in S, if A presents in S and B presents in S, what happens? So, closed interval AB equals S. Then S equals closed interval AB. If A is out, if A presents in S and B is outside of S, then A presents in S and B is outside of S, then S equals closed open AB. By definition. Similarly, the next condition is if A outside of S, B presents in S, then S equals open closed AB. If A and B are outside of S, then S equals open interval AB. So this is the first case. Okay. Yes. Now come to the second case. First case, S is bounded, means it is both bounded above and bounded below. Now come to the second case. In second case, we discuss if S is bounded above but not below. Okay, second, yes, bounded above but not below. Yes, bounded above but not below. Bounded above means by the supremum property or by the completeness property, S has a supremum. So, S is bounded above, supremum of S is let B equals supremum of S. B equals supremum of S. Then S is a B is a supremum of S, then S is a part of open interval minus infinity B. Agree? Minus infinity B or minus infinity closed open closed minus infinity B. Let's set the following. Let's set following minus infinity B. That means set the strictly less than, set the strictly less than B. Set strictly less than B. Now set less than B, consider set less than B, but what is B? B is supremum of S, that means set is not an combines, so set is not an upper bound of S. Therefore, since set is not an upper bound of S, by the previous argument, there exists some y fall in S such that z less than y less than b. Z less than y less than b. But S is not bounded below. S is not bounded below. S is not bounded below means, come on, S is not bounded below means Z is not a lower bound. Z is not a lower bound. Z is not a lower bound means there exists some x such that x less than such. Means x less than such but z less than y, so it is x less than combines x less than z less than y for all x comma y fall in S. For all x comma y fall in S. That means z fall in open interval x y, but which is a part of yes. So, but z is chosen from the minus infinity b. So finally we have minus infinity b is a part of S. Minus infinity b is a part of S. So if b presents in S equals minus infinity close to b, and if b is outside of S, then S equals open interval minus infinity b. Okay. Yes. Now we discuss the next case. S is bounded below but not bounded above. The next case is S is bounded below but not bounded above. Bounded below but not above. Since S is bounded below means by the completeness property its infimum exists. Infimum of S exists. So let A equals infimum of S. A equals infimum of S. A equals infimum of S means what is S? So S is a part of closed open A infinity. S is a part of closed open A infinity. Now as usual, let set the following A infinity. Let's set the following A infinity. Set the following A infinity means surely set greater than A. But what is A? A is the infimum of S, means that is not a, that means that is not a lower bound of S, lower bound for S. But that is not a lower bound for S means there exists some x following S such that A less than x less than such. A less than x less than such. But what is S? S is not bounded. S is not bounded above. S is not bounded above means there exists S. That is not an upper bound of S. That is not an upper bound of S. That is not an upper bound of S means there exists some y presence in S such that y greater than such. So there is y greater than such and a less than x less than such. So what do you get? Then x less than z less than y. X less than z less than y. X less than z less than y for all x comma y following S. That means z following open interval x y, but which is a part of S. Agree. But what is Z following A infinity and Z following S? That means open interval A infinity is a part of S. That's a part of S. So when A presents in S, it is closed open A infinity, and when A is outside of S, it is open A infinity. So closed A infinity equals S means minus A S infinity. So A infinity is a part of S, is a part of A infinity. So A infinity equals S. When A presents in S and A is outside of S, there arises two cases. So this is the third one. And the fourth case is S is neither bounded above nor bounded below. It is not bounded above and not bounded below. Case 4. Not bounded above and neither bounded above nor bounded below. Let's set the following R. Set is any real number. Let's set the following R. Then since it is not bounded above, set is not an upper bound. Set is not an upper bound. Set is not an upper bound means there exists some y following S such that y greater than such or z less than y. Okay. Again, Z is not a lower bound for S. Lower bound for S means there exists some x following S such that x less than such. So means it is x less than z less than y means Z following open interval x y, then it is given it's a part of S. Agreed. Z following open interval x y is a part of S. So where Z is following, but Z following R, and Z is a part of S, hence R is a part of S. But we know that S is a part of R. So it is given S is a part of R, that means R equals S. R equals S. What is S? Means S equals R, but actually what is R? R is open interval minus infinity, infinity. Hence, in all of these cases, S forms an int. So, this is the characterization theorem. There are 4 cases. S is bounded, means it is bounded above and below. And the second case is it is bounded above but not below. Third case is it is bounded below but not above. And fourth case is S is neither bounded above nor bounded below. And we see in 4 cases, in each of these cases, this S forms an interval by using different arguments. Okay, right. So this is the characterization theorem. The theorem is a well-known theorem. Now we define the nested intervals. That's in next class.